Okay, thank you all for being here and staying for the last presentation of this afternoon, which will be about unresolved observation of molecular gas, molecular clouds, and what can these unresolved observation tell us about the internal dynamics and structure of molecular clouds. So why unresolved observation, you may ask? Well, as Jerome said at the beginning of the afternoon, the observation and study of molecular clouds can be simply divided in two categories. So Milky Way observation, everything that's in our galaxy, and extragalactic observation, everything that's outside. And so in the first case, the observations are usually considered spatially resolved, which allows to do complex analysis about the structures, dynamics of molecular clouds, like Jan did. But on the other hand, for extragalactic observation, this is simply out of reach because the linear resolution is at best about 50 parsec. So the spectra, the observation that we get, they are an average of a complex mix of different environments, different structures, and different dynamics. So the question here is very simple, and it's whether we can retrieve any information about the subbeam average dynamics and structure of clouds from unresolved observation. And if we do so, do different traces, do different molecular line emission, tell different stories. So to try to answer this question, we use the ONB dataset. So as we said, a very good observation of molecular cloud with excellent linear resolution and a great number of lines observed. But it's a single cloud with fixed dynamics and structure. So we don't study ONB itself, but we use it as a means to generate a large sample of artificial molecular cloud observation, for which we know both the structure, dynamics, and unresolved observation. So we can study the link between the three. So to make such artificial clouds, we use what's called fractional Brownian motions. So these fractional Brownian motion, or FBM images, have random phases, but they are characterized by a power law slope of the power spectrum. So they are entirely characterized by the parameter beta, and we use them to generate velocity fields and current density fields. And we didn't choose these FBM structures randomly, but specifically because they naturally arise in isothermal supersonic turbulence, which is, broadly speaking, the main mechanism shaping the dynamics and structure of clouds. So when we have a velocity field and a current density field, we then combine those with the ONB data to create a 3D data cube. So to put it simply, we sample spectra from ONB, and then to each pixel of the current density field, we assign the ONB spectra with closest value. So that gives us a first data cube, and then we shuffle, we rearrange this data cube along the spectral axis so that it matches the velocity field we generated just before. And that gives us an artificial molecular cloud. So this is an example. Here you can see ONB in 13C120, and here an artificial molecular cloud in 13C120, and this is the integrated intensity. So we repeat this process about a few thousand times, and that gives us a data set that we can work with the beta of the current density field varying between 2 and 4, which are values commonly found in Milky Way clouds. And then the velocity field beta varies between 2 and 4 also. And it's very important to note that all our clouds in our dataset have a fixed size of 20 parsec and a fixed velocity field amplitude or range. So you can start by taking a look at the cloud average properties of our clouds. And so this here shows the distribution of the cloud average line widths of our 3000 clouds, and for different emission lines. So 12CO, 13CO, 8CO+, so they are ordered by approximately by the gas density price. And there is basically two different behaviors. If you look at 12CO especially, and a bit less 13CO, they have the highest cloud average line widths, but they also show the least amount of dispersion. And on the other hand, if we look at the denser gas traces, not dense gas, but denser, like HU+, C18O, CS, they show much lower line widths, but much more scatter, to the point where you could have a cloud which has the same line width in 12 CS and in 13 CO. And this is mainly due to the spatial distribution of the emission. If you look at 12 CO, it's spatially very extended. So it covers most of the velocity field of the molecular cloud. Yes. And so the cloud average line width then tends to be directly proportional to the range of the velocity field. And on the other hand, for the denser gas traces, they tend to be more concentrated in filaments, in clumps and core. And so then their line width depends very much on the position of these clumps and core in position velocity space. To give you an example, if you have two cores, if they have the same relative velocity, their line width will be much smaller than if you have the two same cores, but with very different relative velocities when you average everything. So yeah, this is the first point, is that the line widths of dense gas traces that are very used in extragalactic observation, as Miriam said, their line widths and so their peak temperature can vary very much just because of the subbeam distribution of the emission and not because of variation of the cloud properties. And if the line width varies very much, we can try to take a look and see if the shape of the spectra varies with the distribution of the emission. So this plot on the right shows how well the cloud average spectrum can be fit by Gaussian. So the y-axis shows the sum of the residuals. And if the sum of the residuals increase, the fit is poorer, so the spectra is more complex. And as you can see, if we increase the index of the velocity field, the spectral complexity increases. And this is especially the case for denser gas traces such as CO or CS, and not really the case for 12 CO in blue. And we can do the same kind of plot, but this time on the x-axis is the column density field, and we can see here that there is no effect whatsoever. And so this hints to the fact that the denser gas traces can give some information about the subbeam velocity field, and especially about the predominant scale. If you have a low beta value, this means the velocity field is mainly on small scales. Larger beta means larger scales. So yeah, in conclusion, if we separate the result in bulk gas and denser gas, so bulk gas being 12CO and 13CO, we see that the line parameters are not sensitive to the subbeam gas structure, which is very reassuring for extragalactic observer, where this was kind of a potential issue and a friction within the field, because some people thought that all the cloud parameters that were derived from 12CO might be very varying purely because of the subbeam distribution of the emission. And on the other hand, this shows also that the line width is a good measurement of the velocity field amplitude, and so the turbulent energy of the cloud or in the pixel. And on the other hand, for denser gas traces, it's the opposite. There is a very large variability of the parameters with the subbeam gas distribution, whether the line width and so also the peak temperature. But this also means that we can try to retrieve some information about the subbeam velocity structure from this spectra, from these denser gas traces. So future work includes trying to investigate a bit more in details how much of the information about the subbeam velocity field we can infer from the denser gas, line profiles. And then the main piece of work will be to try to retrieve the statistical distribution of the subbeam current density using a method very similar to what Pierre used, and ultimately relate this to star formation rate and efficiencies. And that's all for me. Thank you very much.
Thank you. Questions? Yes.
Well, it's a more technical question. I mean, you're comparing different traces of different practices. Are you considering bringing everything to the same angular resolution?
They are the same angular resolution. So when I say universal dynamics, when I create my artificial clouds, all the pixels are about the same resolution, but the size of the cloud is about 20-30 parsec. So in this case, all the tracers have the same angular resolution.
Yes, I have a question on this plot. How do you get that CS, for example, traces less dense gas than HCN? Because in
you shouldn't focus too much on this. It's very approximate. I don't try to order them in detail very by the gas density traces, more like 32 and then the rest.
So this is not from the RIMP data, no?
Yeah.
It is not.
I see that. Yeah, this is from the RIMP data, but this is very approximate, so you shouldn't take it as like CS traces.
Yes, and HCO plus should be with certain CO, not with the others. So
yeah.
This
Only according to the extension of the emission.
Yes.
Is different. They are
different, yes.
Okay. And another question: when you talk about the line width analysis, you mean the observed line width analysis, or you take into account the mass of the molecule?
No, the observed lines.
Because for the same temperature, a molecule that is more massive has a narrower.
Yeah, in this case, it's a single temperature. It's a distribution of temperature in the cloud, and it's the temperature distribution of Orion B. And all the different clouds have the same temperature distribution.
Thank you, Antoine.